So in this little segment, we're going to look at how the E versus K diagram that we just derived from the Kronig-Penny model relates to wave propagation. So we're going to go back to the basic definition of a wave. So this represents a traveling wave which will move to the right versus time. And how do we know this? Well, we can pick a certain fixed point here. Let's imagine this is, since this is a cosine, the convenient place to cut it is at x equals 0 at t equals 0. And then we'll redraw at a certain time later. And what we're going to do is look for the point here where this entire argument equals 0. And this time we're going to say is delta t, and we're going to see that this wave has moved delta x in the right-hand direction. So we're going to follow a point of constant phase on this wave. And constant phase means that this argument has a constant value. So if we look at that equation, and then we take the differential of the equation, oops, sorry, that's a minus. We can figure out what's known as the phase velocity from this. So the phase velocity then is the velocity at which a single harmonic wave travels in the crystal. Or in terms of what we talked about in the quantum mechanical free particle picture, it's the velocity at which a single free particle state will move through this crystal. We can also define another velocity. I'll skip the derivation here, but it turns out that we can define what's known as a group velocity. And this is the velocity at which a superposition of waves will move through the medium. So for example, if we take a large number of these harmonic waves and create a Fourier series, let's imagine that it represented a square wave. And we're representing this as the sum of u, k, times some amplitude factors. So we built this square wave out of lots of harmonic components, as you've seen in Fourier series before. And the group velocity is the velocity at which this superposition will move. And in quantum mechanical terms, this helps us to resolve this paradox between whether an electron should be treated as a wave or as a particle. A particle we can localize, we know where it is. And a wave, we don't know where it is, but we know how fast it's going. And I say we don't know where it is because this cosine function extends all the way from negative infinity to infinity. So if we instead think of our electron as a wave packet, we can resolve that seeming contradiction. And that means that it'll travel at the group velocity. So we've defined the phase velocity and group velocity, and then let's look back at what this EK diagram has to do with these waves. So we have to write some definitions first. We saw that the energy can actually be represented as h bar omega. If we look at the time phase terms in a complex exponential, they're written like this. And if we take e over h bar, we can rewrite it as plus or minus I omega t, like we're used to seeing in phasor representations of all sorts of waves like voltage or current. We can also remember that the velocity is the momentum over the mass, and the momentum is in quantum mechanics given by h bar k. So if we look at a free particle state for an electron, we're going to have the relationship that E equals p squared over 2m, which equals h bar squared k squared over 2m. And this describes the parabolas that we talked about a moment ago, especially if we introduce this effective mass. So the E versus K diagram is sort of a generalization of this. So we have our E of K, which is a little more complicated than this parabola. We know that it has some other shape, but we can represent it as this parabola near the conduction band edge or the valence band edge. So the true EK diagram then is really showing us the dispersion relation for the electrons in the crystal. And what do I mean by dispersion relation? So the dispersion relation tells us how these waves travel inside the medium. Let's now make the connection between the group velocity and the phase velocity and the E versus K diagram. So I've been talking in terms of E versus K, but I could also just represent the same diagram or the same functions, which we would usually picture like this, instead on an omega of K axis here versus K. And all I had to do there was divide by a constant h bar. So this might represent our conduction band. This would represent our valence band here. So if I want to calculate the phase velocity of an electron in the conduction band, what I need to do is just calculate the amount of kinetic energy that the electron would have divided by its K value. And I could do that at any point along this line. And I said kinetic energy there, and that's important. So one of the things this E versus K diagram tells you, it's representing the total energy of the electron. But from the edge of the valence band to the edge of the conduction band is our E gap. And this is really potential energy. So the kinetic energy is measured for the electrons in the conduction band from this reference point here. So we can calculate the phase velocity for any point along this line just by taking the omega of K minus E gap divided by k. And that's really what we've done here with this triangular construction. Now, if instead we want to take the group velocity, we end up taking the slope. And the slope here we don't have to worry about. We don't have to worry about this constant term. We can just take d omega of k dk. And this is equal to our v group. So what this diagram says is that we can, by looking at at this green function, the actual dispersion relation, we know how each plane wave state moves through the crystal. So we had our representation of a wave, which I'll represent as psi equals a cosine. And now I'm going to write it out explicitly that omega is a function of k times time minus kx. So this green curve actually tells us how fast or slow the individual harmonic waves move for any value of k, or how fast or slow a wave packet representing our electron would move through the crystal. So let's relate this back to the solutions that we guessed for the Kronig-Penney model, just to tie everything together. So for the Kronig-Penney model, we guess that the wave function in total can be expressed as a u of k and x times e to the I kx. So this part here is our harmonic wave, and then this part here is a little modulation on top of it. Let's consider it sort of like a carrier wave and a little modulation. So what we're trying to do here is really represent the true solutions to the Schrödinger equation, which are a little more complicated because of these little wiggles that are introduced by the fact that each atom interacts with the electron as it's going past. We're really trying to represent that more complicated wave function as a plane wave. And so we can write the total plane wave, x and time, we can write it out like this. And these two exponentials here could also be represented in the cosine form that we just looked at. So we're going to sort of ignore these little wiggles and treat the solutions to the Schrödinger equation as if they're plane waves. And that's what we can relate back to the dispersion relation. So the dispersion relation, omega of k, can be used to calculate the phase velocity and the group velocity for these traveling wave solutions inside of this periodic arrangement of atoms. And this omega of k encodes all the information that the crystal of the constraints the crystal makes on these solutions, including what these little wiggles do in terms of allowing or disallowing different energies. To summarize this section again, what we've looked at is the relationship between these solutions to the Kronig-Penney model to fundamental wave propagation. And we saw that the Kronig-Penney model tells us not only where the bands and band gaps occur, but it also encodes information about the phase velocity and group velocity of plane wave solutions inside the crystal. So The carrier wave is what you should think about. We're trying to represent the electron states as wave packets constructed of superpositions of these pure harmonic carrier waves. And the U function, which we ended up solving for inside the total solution, is sort of sweeping a lot of the details of what happens to the wave functions under the rug. And it basically introduces these little wiggles on the wave function every time the different atoms in the crystal are passed.